How's it going, everyone? Welcome to Luis Gonzalez here. Today let's going to explore now this topic called closures, something that I'm quite familiar with. In fact, I start to understand and apply this closure concept 8 months ago. So also the reason why I'm looking at the functional light, a course taught by Carl Simpson, is because I want to have this deep understanding and be able to describe how and why we're doing this kind of stuff, especially if you need to provide this solution to somebody else, to your clients. And well, if they ask you questions, you know where those come, that you know the answer. Now, because of that, all right, we went through describing the introduction of FPE, of functional programming. What is the value proposition, which is the code is provable, since now it is layout on mathematical proof that allow us is to have high level of degree when we use those kind of tools, so we can focus our attentions on those areas that we are not that confident, such as database queries, DOM operations, network calls, timestamp, random generation numbers, or anything that has CPU or generates CPU hits or CPU time delay. So there is of course a learning curve of this, and especially the approach that Carl Simpson took is something that I really love about this. Let's going to use what we already know, the imperative paradigms, and then we progressively going to learn how to apply those FP concepts and tools, so then our code will not only becomes much more readable, but we have now the applicability of each one of those concepts and when to use it. So this is the introduction, all right? And the value proposition of functional programming. So unlike other courses out there that teach you is from the ivory tower, especially from functional programmer, when they assume that you have and you know a lot of mathematical concepts and fundamentals, this is one of the thing that I love about this course of Carl Simpson, so that's great. That's absolutely great. And for that, we first need to understand what is a function and a procedure. Again, in today's video, we're going to focus our attention on closure. We're going to make a quick recap of all of this, all right, about the function purity. What is a function is the semantic relationship between it is input and it is computed output. And unlike procedures, functions are needs to be pure. This is part of the rules that we need to, or the constraint that we need to set if we want to take advantage of the FP, the provability of our code. So, function purity. So this is a function, this is a procedure. A function must not alter the state outside of the function, and because of that, we need to define is what are the stuff or the side effects that cause that, something that I previously mentioned, or that I mentioned before. So this set of rules of the no side effects in a functions, and to reduce the reassignment area into is one single input, one single output. The same input, the same output. It's just to increase the level of confidence that when we need to write our functions, and by the time we call it, we know that will behave as expected. It won't change the state of the program in an unexpected way. So sometimes we don't have that privilege to do. So how can we now extract the impurity of those functions? So there's two techniques to do that. One of them is containing the lexical scope at functions definition, all right? And the other is at function call is to now take a snapshot of everything and then restore the state afterward. So those two techniques that depend on your use case can be quite cheap or expensive to implement. So it is up to you when you can use it, especially if you are working with functional programming on the front end. You might see the benefit of doing that. But in any case, so then we look at another important concept, which is the argument adapters, and how now the functional programmers are obsessed with the shape of the function, which is pretty much like you have different Lego pieces. When you stack one on another, or when you want to make two different Lego pieces fit each other, right? So this arguments and parameters. So argument is the value, are those values that we pass when we call the function, and the parameter is the name of the inputs from the point of view, from the function point of view definition, right? So this shape of the function, which is technically speaking the type definition, is something that will allow us to, from the functional programming, will allow us to now interchange or change the shape of these functions. And the shape of this function is what are the inputs, what are the number of things and the shape of the things that we pass in, and the number of things and the shape of the things that come out of that function. So why this is important? Because sometimes you want us to have a function, and functional programmers love is functions that have one single parameter or unity. Those, and the most favorite functions that functional programmers love are binary functions, all right, with two arguments. But sometimes you need to have more arguments, right? And this is called now the n-additive, the number of arguments that you're going to pass to a function. So since the idea of this arguments adapters is to see that how you can play with the arguments in your function, or with the parameter of your functions. Sometimes you want to flip the arguments if this is a binary function, or sometimes you want to only get is one value, all right? Now, this argument adapters is just to understand that how now functional programmer in libraries actually works, so you can get yourself familiar with this argument adapters, and if you find yourself in the need to develop your own, you can is create some, make a peer to those libraries, for example Randa, and collaborate with that. Why this is important? Because we as a community, we need to get ourselves familiar with that, right? So it's like you go into, so you have a toolkit for manual stuff in your house, right? So you had a handy toolkit, right? So if you see a piece that you have never seen before, you don't know how to use that, right? So that's the idea of make a peer of those libraries if you find yourself in the need of using that. So we'll look at the flip, the reverse, argument adapters, and another concept from functional programming, which is pure function, point-free style. So for those who are not familiar with this point-free style, is if you go, or if you remember your 8th grade math class, so you have something called the point-free or the fixed point, where, for example, if you want to draw is so some teacher tells you, is like, hey, wouldn't it be nice to actually is fix a point in this graph in y and g, y and x, fix this point in here to see what we're going to draw, right? So most of the time when you fix a point in whether it's a y or x axis, so you draw a line, right? So why this is important? Because with point-free techniques, all right, where the value proposition is that it gives us the ability to describe a function's relationships without describing these data points, without describing it as inputs, all right? As long as they have the same shape, all right? As long as one function receives the same number of arguments, or return the same number of arguments, as long as they have the same shapes, we can now describe that in terms of its relationship. So this is when now the readability of our code increase, because you might mistakenly take that for an identifier, whether it's a variable, a count, or other stuff. The thing here is that when you fix here, and also we look at particularly advanced topics of point-free, it's like when you fix a higher order function, a utility function, right? Let me see if I have this. So for example here, let's say we have these two functions, right? You have now two utility functions, models and equal, or any other utility function. For the sake of the example, this one, right? Where you say, hey, I want you to now fix this utility function general purpose to be more specific, okay? And by the time that I want to use that, I can assign that to a variable that of course is going to give me a function that receives one parameter, for example mod2, and any time that I pass this this function's reference to other functions arguments, now it'll be much more clear the relationships when I do this. So for example, if I want to use these two functions, okay, to get something specific, all right, I can do that where we can define is another utility functions or high order functions, which is a fancy name to say, hey, functions that receive functions or return functions. We can define is another high order function, a utility function here, that is going to take those two functions, all right, and then it will call that. So the arguments of the second function, or the arguments of the second function will be so the argument of the second function will be the returning value from the first function. This is something that is known as composition, and something that we're gonna see a lot in there. So instead of defining this like this, so equal one, or in terms of it is that a point, we can define them in terms of it is functions definition, right? So we remove the data point, we remove that stuff that are not relevant for the relationship, and we can focus our attentions on this readability. Again, I know that there are some implicit stuff here, and as a programmer we preferred, if you ask programmers, I will argue that 95 or 97% of programmers actually prefer to be more explicit than implicit. But with this, by using now this concept of point-free, so by being implicit, we are now gain readability in our code and see the relationship between our code. So this is what we are doing here. Again, this is in terms of it is function, in terms of this functionality, in terms of this function purity, right? Because we can also have in terms of this, for example, okay. Yep, we can have also another relationship here. For example, like not, which is another higher order function to say, hey, anytime I receive this function and it is arguments, I want to know is the output negated, okay, which is something that we are looking at here. Not is odd, all right. So give me the value so give me the even value, or is even value, all right. So this is quite interesting because it matters not only what kind of input we receive, but the order, but what order are lists in. Yep, but what order are lists in. So let's go to now dive in closures and the exercise here. So now things slowly but progressively started to make a lot of sense, especially if you are able to describe this. Absolutely, absolutely. So let's get into this.
All right, so we've already hinted at the idea of closure in this course. A couple of times we've already used it. But I want to be very specific about a definition for closure, because there's a lot of misconception about this concept, and it is absolutely essential. You just cannot do functional programming without a solid understanding of closure. So I want to give you a very specific definition for closure that is based upon what we can observe in our program. And that is, closure is when a function remembers the variables around it, even when that function is executed off.
But it's from the it's from the function point of view. So so closure is when a function remember, or well, remember quote function is when a function remember the variables around it, even when the function is executed elsewhere. All right. So this is a closure, right? So it's when a function remember the variables around it, even when the function is executed elsewhere. All right. So yeah, this is a fundamental concept here that unlock is, for example, other patterns, for example, like model patterns. All right, that you are now able to enclose all of the variables, all of these identifiers, all of this stuff that you store in memory around it, in even after, or even when the function is executed elsewhere. But it's from the point of view of the functions. it all start as the function. So closure is when the function remembers all the variables around it, even when even when that function, okay, even when that function is executed elsewhere.
Variables that you access outside of the function. They aren't directly passed in. They're accessed, like, for example, when we access global variables. Anytime you access a variable from an outer scope, and then you take that function that is doing that access and you pass it somewhere else, and you run it in a different scope. If you thought about it logically, you'd say, well, it should forget about that variable because it's running in a different scope. But it doesn't forget about the variable. And the reason it doesn't is because of closure. And if that sounds too abstract to you, let me remind you that we've already seen this several times in the code we've looked at. Here's an example. I'm illustrating the idea of closure here. I have a make counter function. Make counter doesn't take any inputs in. It declares a variable line 2 called counter. And it returns us back a function, which every time we call it, is going to increment that counter variable. So on line 8, I make my counter. I say var c equals make counter. And I call c with no inputs, and I get back to value 1. And then I call c with no inputs, and I get back to value 2, and 3, and 4. So it's in a counter, right? It could be useful in our program to have a counter. Let me ask you, this is definitely closure because we have the inner function increment closing over that counter variable. It's remembering it. Even though make counter has finished, the C function still remembers it and can still keep updating it. That's how it works. That's called closure. But I want to ask you, is the C function a pure function call?
No, because it doesn't return the same value.
Are those pure function calls? It's not pulling from the dollar. We are not getting the same output. We're passing in the same input, which in this case is million. But every time we're getting a different output. So it absolutely violates one of the fundamental premises of a pure function. So here's the takeaway. Closure is not necessarily functionally pure. But closure can absolutely be used functionally. So the key is, if I'm closing over a variable, this counter, it can't be reassigned. It's not necessarily functionally pure.
So closures are not necessarily pure. Are not necessarily functionally pure. That we can make it.
But closure can absolutely be used functionally.
But closure can absolutely
If it's getting reassigned every time,
be used.
Because now we are not closing
But closures can absolutely be used
in which case we now have a pure function.
in a pure way.
Because now we are not closed over a variable, this counter can absolutely be used in function mode. So the key is, if I'm closing over a variable, this counter
Period.
can't be reassigned. If it's getting reassigned every time, that's a big no-no, because now we are not closed over a constant anymore. We're just closed over some changing state, in which case we now have a pure function. You might have to do that if you program it, but that's not going to be a pure function. So let's look at some examples of using closure that is consistent with functions, that is going to produce. Remember unary? That was one of the first utilities we looked at, our first higher order function. It takes in an fn, and it remembers that fn, and it uses it later. How does it do that? Why did the fn variable from line 1, the parameter, not get garbage collected when unary finished? The answer is because the inner function 1, which got returned, is holding on to that parameter via what we call closure. It still has access to that. So later on, whenever we call f somewhere, it still remembers the original thing that was passed in. And that's not the only example we saw of closure. Remember add and other? We talked about this one. Remember how it's referencing that z variable, even though that z variable was passed in an outer scope? The add to function is closed over the variable z, which is why it's able to use that later on. And the key thing here is that in both of those slides, the fn on the previous slide and the z on this slide, in both of those cases, we are referencing a variable outside of ourselves, which seems like it would be a no-no, but it's safe functionally because it doesn't change. It's a memory over a thing that doesn't go on. That's what makes it still functional. Let's do a practice exercise on this topic of closure. It feels like a really important topic. We're probably going to keep coming against it over and over again in functional programming. It's good for us to get some more exposure to it. In this exercise, we're going to practice closure by building a utility using a little strings. We're building up a utility that we'll call string bulk. If you look at the exercise, it's good for us to get some more exposure to it. In this exercise, we're going to practice closure by building a utility using a little strings. We're building up a utility that we'll call string bulk. If you look at the exercise, specifically looking at the test cases down at the bottom, you'll see what this is supposed to be able to do. It's supposed to be able to call this function, string builder, and pass it a single string. And then if we call it again with another string and another string and another string, we can just keep adding more and more strings to it until we call it once without any input. And then it's going to go back and concatenate all of those strings together to give us one final string. And Also, not only will it do that, but we should be able to capture those individual specialized functions. So we should be able to capture, for example, hello is the intermediate function after string builder was called with hello. And we should be able to call this twice, producing two different functions, in this case Kyle and Caesar. And then we should be able to call Kyle again, and when we call it with nothing, this question should come back with an actual string. Okay? This is a bit of a challenging exercise. A little bit of a hint can be seen in the README, so you should definitely check out these hints. Should be able to give you everything you need, but it will be a little bit tricky and challenging. Make sure all of the test cases pass. Let's talk about the solution to our exercise on closing. Now I am just
All right. Or even here. Yeah, let's go to getting here. To GitHub. That's right. Functional light here. As it is. There are some point-free challenge here. And let's going to merge this. And let's going to now create is a new branch for closures. So git pull, fetch me everything here, and git switch to git switch a closure. Alright, now on closure we can create this folder called closure. Alright, and then inside of this I want you to now is whatever we have on here, I want to paste this here. And let's go to read this here, right? So let's get into this. This is an exercise to practice closures, instruction, modify string builder so that it can take a string and return back a function. Okay, note, for the purpose of this exercise, assume that string builder itself is always called with a string initially. Okay, for each call to be a function here, if a string is passed, a function should be returned. If a non-string is passed, such as passing no arguments, a string value should be returned, which is the concatenation of all of the passes in a string. You can use a type of foo equal to string to test if foo is a string. And look at the test case at the bottom of the exercise file to clarify any question about expected behavior and ensure your functions are pure. Let's get into this, which is go. And there you got it. Alright, we were reading about instructions. So we're gonna modify is a function called string builder, like this, so that it can take a string and return back a function, right? So you're gonna return now a function. Okay, you're gonna return himself. That's interesting. For purpose of this exercise, assume that string builder itself is always called with a string initially, which is pretty much like point-free style, right? Of a fixed point. You're gonna fix these functions to call with this argument. All right. So for each call to a function here, if a string is passed, a function should be returned. So if a string is passed, so if the string is equal to string, right? So if a string is passed, but in this case you have to check that out with type of. So if a string is passed, a function should be returned, right? A function should be returned. If a non-string is passed, so just passing no argument, a string value should be returned. A string value should be returned, which is the concatenation of all of the paths in string. But this is interesting because you say, hey, I'm going to return is now is the string. All right. If it's not on a string, then I want to pass now whatever you have on a string plus the concatenation of the string builder at that moment. Right? And then of course I will need to return that. Should be returning with the which is the concatenation of all the past string. Just return it. Right? So, string builder. If a known hints, you can use type of food to equal to string to tell if food is a string. Look at the test case at the bottom to exercise files to clarify any question about expected behavior. Ensure your functions are pure. Avoid mutating a closed over variable, which will be a side effect. So there is no side effects here because we are working with existing variables in this scope. All right, and it's interesting because anytime we're calling this or this, we are actually is now passing is the value here as a way to now build this stuff up. So it would say, hey, now this is part of the, oh, no, but not like this. I'm going to push this stuff here. And then you say, hey, git add everything. And then git commit to keep track of these changes. Okay. Closure exercise. Okay. And then say git push origin closure. Right. We open a new GitHub PR. Here exploring is recursion with or closure with recursion. Closure with recursion. Closure with recursion in a point-free style. Okay, there you got it. All right, so we got is this one. So by the time that we run this, the first time you say, hey, I'm going to now is hold this string, right? I'm gonna return is a new function, all right, that is the string. Okay, so now by the time that I return this function, I'm going to now have a reference with the updated string value. The same for this, the same for this. And in this case, it's like by the time that I call this function called Kyle, all right, and then I don't pass any parameters, I'm gonna return is now whatever that I have stored previously and the concatenation of that at that point, right? Which is this and whatever we pass here as second argument. And the same for this. That's a way to say, hey, this is now in stop. So this is the string builder hello. So here we're calling is this, and we're passing it as the second argument is an empty string, followed by Kyle, followed by a dot, and followed by that. And ultimately, this must be the same of the hello Kyle, like that. So this, of course, should be work. It will work, by the way. Say XGS node closure it say, hey, if type of because I think it must be as a type. Because it continued to call that. Interesting. So if this is a string, okay, I want you to return is the string builder. It's because there is no stop condition here. And following this example is this. For each call to a function here, if a string is passed, a function should be returned. So I can say is this function so a function should be returned. But if this function should be returned, a function should be returned.
Just going to forewarn you, I am going to deliberately solve this incorrectly to prove a point about the way that we think about closure and what we need to do in order to solve it correctly. So the first thing to note is that string builder, when called with a string, returns back what?
A function.
Returns back another function. That's expected to be called with a string. So it's going to keep returning back a function. And it will do that essentially forever. As long as you keep passing the strings, even empty strings, it's just going to keep returning back a function. So what does that pattern look like? Well, we know at a minimum, we got to make and return a function. So I'm going to just call this function next because it's just sitting there.
Exactly. It's like, but again, this is the pattern here.
We're waiting for the next string. That function is going to receive a string.
It's a function.
Receive a value. We're not sure if it's a string, so we receive a value. Now, I want to keep going. In other words, I want to return a function if the value that was passed in was
A string. Mm-hmm.
Not a string, that's not okay. Okay? But I need to keep track of the strings that I've seen so far. I need to keep returning this thing back over and over. I keep track of those strings in some way. And it seems natural that I might just start concatenating it onto the string. So if I receive value and if I receive a value that is of type,
it's a type of string.
then what I know is that I could just concatenate it onto the end of str, right? And that was my initial string. And I can just start concatenating stuff onto the end of it as I see it until I don't see a string, and then just I need to return a string. That's a convenient way of keeping track of this. So if I just say string plus v, and then otherwise,
that makes much more sense than this, because following is this particular pattern that at the end of the day you need to return is a function here that you can call it next. So anytime you call string builder, you're gonna return you, or it's gonna give you a next. All right. Or at least from this silly exercise. Okay. So we need to find a way to somehow is to keep track of the variables or the values that we're going to pass, the arguments we're going to pass. So one way to do this is by, hey, if this is a string, we say, hey, since thanks to closure we can have access to the outer scope from the inner function, even when, because I want to use those words, okay, even when the function is executed elsewhere, all right. So even if the function is executed elsewhere, but I want to have now a record of this, I want to remember this. Now this is a string and v, so we are actually concatenating that based on that, and we want is to, of course, return this. We want to return is this value, is concatenated value. If it's not, give me a second, please. And we're back. All right. But again, the thing here, at least from this function here, is to say, hey, we want is to, for each call of a function here, if a string is passed, a function should be returned, which is in this case, which is great. All right. However, if a non-string is passed, such as passing no argument, a string value should be returned, which is a concatenation of all the passing string. So instead of passing is this, because the concatenation should be passed, and this concatenation here should be is in fact, if I don't receive any arguments, the concatenation should be passed here, right? So anytime that I'm calling this function like this, I want to do is this. Oh, you must return this.
So in other words, so if it was a string, I concatenated it on, what do I want to do? I want to return that next function. Just the function itself.
And here's when you get me lost. And returning is this next function. So I do the concatenation, and I want to return that function again with the values updated. A string.
Follow that how do I know if I need to keep going with the new function or not? It's whether I pass the string. Now, if I take this code, this is deliberately the wrong solution. I'll explain why in a moment. If I take this code and we try to run it, you'll notice that I get several failed tests. You'll notice something interesting. The test that did succeed is the most seemingly complex of the tests, the one that was called a bunch of times. That one passed, and it's all these ones that didn't pass. And there's a clue there, if you pay close attention, there's a clue there as to why our solution didn't work. And the clue is that what we have are these intermediary functions. Notice I've got Kyle and Sue. Those are sort of a fork, if you will, from hello, where we're going to end up with hello Kyle and hello Susan. But if I have a modified string with the word Kyle, and then I try to call Susan, if this function is closed over that same string and modified string, that string no longer says hello, now it says hello Kyle. And I'm trying to put Susan on the end of hello Kyle. So that's really kind of where our problem is then, is that if you think about it, what we're doing is we're closing over a variable that's being modified. So in other words, we have functional impurity. That's why this is not working. Because we have functional impurity. So I'm going to go back. That string no longer says hello, now it says hello Kyle. And I'm trying to put Susan on the end of hello Kyle. Those are sort of a fork, if you will, from hello, where we end up with hello Kyle and hello Susan. But if I have a modified string with the word Kyle, and then I try to call Susan, if this function is closed over that same string and modified string, that string no longer says hello, now it says
Let's say hello, Kyle.
and I'm trying to put Susan on the end of hello Kyle. So that's really kind of where our problem is that if you think about it, what we're doing is we're closing over a variable. So in other words, we have functional impurity. That's why it's not working, because we have functional impurity. So I'm going to go back and try to solve this in a different way that preserves the function. Okay? Let's start it. I'll leave the function next time. So we know now that we never want string to be modified. We're closing over this thing, which is what is inner function is doing. We want to only close over string that stays the same. Okay? So I do still want to do a test. I want to say if the type of the
So we're going to stay the same.
is string, then I want to do something, and I am going to return something here, so we'll do that. If I don't return the string, then what is it that I want to do? This is the part that's making something here, so we'll do that. If I don't return the string, then what is it that I want to return? This is the part that's making a little bit counterintuitive. Let's talk about what happens if the string is irrelevant. Let's talk about what happens if we have passed a string that is a string.
So if we have passed a v that is a string, so this is the string that we want to concatenate.
str, whatever value that comes, and we don't want to modify string, but what we want is a new function that will wait for the next string, and that new function needs to know about both string and v. So
Exactly. And we need a new function that knows about is a string and view. Why is that? Because we want to create a close over those variables. We want to remember those things. So by returning is a function here.
in other words, what I really want to do is I want to call string builder. I want to actually call it from this time. Now when I call string builder, what is it going to return?
So it's going to return you now is a function. It's going to return you is a function called next that has at that moment is the string, all right, value that is not, we're not passing that.
Return me another function. But when I pass in the string builder is
So the idea of this is that this is string that what we're calling it, we're talking about is now function calling functions definition. So by the time that we call this function with these arguments, it say, hey, now this is this new string that the next function is close over this, is going to hold that variable, right? that we are passing in, and then it's gonna give us is, well, this function.
It's the new partially concatenated string. I'm not modifying the variable that I'm closing. I am calling to the next level. So now this is almost a variable. It's exactly a variable.
Mm-hmm.
String builder comes back in. This string is now going to be the two string. Closed over the two string. We do it again. Now it's a bigger string. We're closing over a bigger string. But every single level of that closure is only ever closing over one value. So what if I didn't get a V? Well, now.
Okay, so if I didn't get a V, now I can return is return the string.
V wasn't a string. It was undefined false. It wasn't a string. And I know that whatever this was last time was the end value of that string.
That is mind-bending stuff, bro. But the thing here is that because this is not working, because this is the first time, and we are actually modifying or mutating is this state, this string. What we want to do is to create a function that close over the previous variables, or the previous variables, all right, so we don't mutate them. So holy moly, bro. So what we can do here is say, hey, if we want to create now a new function that close over that, we say I want to return something here, okay, and this stuff that I want to return is a new function that close over these two new functions. In other words, I'm gonna call this a string builder with this updated values, with this new concatenated versions. And anytime you call next, you have now a more piece of it, and you call next a new piece of it, and call next a new piece of this. But the thing here is that with this, all right, functions here, by the time that you call this string builder with this new updated version of that, you have now entered here into a new realm with the new updated value. This is quite like recursion, and the end of this is when we don't receive, because this is pretty much the stop condition is when this is not like that. Okay, this is the stop condition. But here you're saying, hey, I want you to now buy. If you don't if the argument, if the value that we're receiving is not on a string, okay, then I want you to now, whatever you have stored previously on any function call, I want you to give me that. This is mind-bending stuff, bro. This is mind-bending stuff. And the thing here is that we're using is the same functions on the function definition and then on the function call. And by the time we call this function, we are closing over these two functions here. So we are not creating a new one. So we are not mutating a new one. Instead, we are calling that. And by calling this with this new updated value, so this is pretty much like a machine. So you're calling this. Initially, you're calling it with this string, all right? And then with a new string there. If this is a string, of course, it's going to now call is the function with this new updated part, all right? That now has stored that. And you're going to continue to do that, and so on, so on, so forth, until it finds is that parameter that you pass is an empty string here, or is you don't pass any argument there. And when you do that, all right, now I'm going and now I'm gonna give you is the string that I have from all of these concatenations. Oh my god, that's pretty mind-bending stuff. And that'll be all for this video. Take care. Bye bye.